Thanks a lot to the organizers for the opportunity to speak. I noticed in the other talks that maybe people trickle in for the first couple of minutes, so I'm going to waste some time by, well, I'm the last speaker, so it's my obligation and also my pleasure to have us all thank the organizers. If we could all thank them for their efforts in organizing this year after year. It's a really high quality Zoom conference, so I'm glad it's still around. All right. And with that, yeah, so I'll get going. So what I'm talking about today is joint work with Alan Knutson and Mario Sanchez. And I'm mostly going to talk about the permutahedron and some subdivisions. I'm going to say a little bit about the degenerations, but not too much, mostly just like if you're interested in that stuff, we could talk more about it later. Okay, so, right, I guess the only maybe disadvantage of, well, there are many advantages of Zoom conferences. One disadvantage is that I'm not sure how many of the other talks you've been to, so I'm going to review some background that has already been gone over. Oh, well. But the first thing I want to talk about is just what is the permutahedron. So there's one for each n, so fix n. The permutahedron is the convex hull of all permutation vectors in R to the n. Right, so by permutation vector, I mean, well, you pick some permutation in Sn, you write it in one line notation, and you treat that as a vector. Right, so here's perm 3. So I'm looking at the elements of permutations in S3. So I told you, and also it's obvious, right, these vectors are in R3, but actually this whole polytope is living inside of a single hyperplane where the coordinate sums are equal to 6, so it's actually two-dimensional, and that two-dimensional picture is what I've drawn for you here. Okay, and then here's perm 4. So I've just drawn the permutations, but you should be thinking of these as vectors in R4. Again, they all live in some hyperplane. And so there, it's actually a three-dimensional picture, and that's what I've drawn. Okay, for later, it may also be useful to think about this as perm 1 to ... n. So like I've taken the vector 1 through n, and then I've permuted it in all possible ways, permuted the coordinates in all possible ways, and taken the convex hull. Okay, so I'm going to be interested in some very nice decompositions of the permutahedron into some smaller polytopes. And to define those smaller polytopes, we need to remember the Bruhat order. So remember that permutations have a statistic called length, which just is the number of inversions of the permutation, or the number of pairs of numbers you see out of order in the permutation. And using this, we can define the Bruhat order. So U is less than or equal to V in the Bruhat order if you can get from U up to V by a sequence of transpositions which increase length. Right, and so transposition is I take two numbers that appear in the permutation and I just swap them. Okay, so here's a picture of the Casa diagram of Bruhat order for S3. So all I've drawn here is cover relations. And right, so moving up the edges always moves you up in Bruhat order. And so, right, we see, this is maybe not a very interesting example, but the identity permutation 1, 2, 3 is less than the permutation 3, 1, 2 in Bruhat order, for example, because I can go from 1, 2, 3 to 2, 1, 3 by a length increasing transposition, right? So when I swap 1 and 2, that increases my length. And then I can move from 2, 1, 3 up to 3, 1, 2 by swapping 2 and 3, which is another length increasing transposition. Okay, so with that, we can define our smaller polytopes. So these smaller polytopes are called Bruhat interval polytopes. And these were first defined, I think, by Kodama and Williams, but the definition is supernatural. Maybe they could have even been defined earlier. So pick a pair of permutations, U and V in Sn. And the Bruhat interval polytope, PUV, is going to be, well, the convex hull of all those permutation vectors where the permutation Z is between U and V in Bruhat order. Okay, so yeah, so instead of taking the convex hull of all permutation vectors, I'm just taking the convex hull of those in a particular Bruhat interval. Okay, and I said pick an arbitrary pair U and V, but of course, if U and V aren't related in the Bruhat order, if they're not comparable, then this will be empty. So yeah, I can think of these as really being indexed by Bruhat intervals. Okay, so some examples of Bruhat interval polytopes. One of them is just the permutahedron itself. So that's the Bruhat interval polytope indexed by the identity at the bottom of the Bruhat order, and the element W0 at the top of the Bruhat order. So W0 is the permutation that reverses the numbers. Okay, so that's just this, what permutations are between these two? Well, all of them. I've just got the permutahedron. For other Bruhat interval polytopes, well, okay, so here's a reminder of what the Hasse diagram for Bruhat order looked like. So, okay, well, all of the vertices of the permutahedron are themselves Bruhat interval polytopes, and so are all of the edges. So all of the edges correspond to Bruhat intervals. And then here in these pictures are all of the other Bruhat interval polytopes in S3. So yeah, right, we have these two edges, and then also these four quadrilaterals. Right, so those are Bruhat interval polytopes. A couple more facts, maybe good to keep in mind. All faces of Bruhat interval polytopes are again Bruhat interval polytopes for some subintervals. The converse is not necessarily true. So if you have a subinterval, it may not correspond to a face of your Bruhat interval polytope. It might be somewhere inside. Okay, and this fact about faces is a theorem of Zuckerman and Williams. If you like algebraic geometry or the flag variety, you may also want to know that this Bruhat interval polytope is actually the moment map image of a particular Richardson variety in the complete flag variety. I'm not really going to say anything more about that, just if you like polytopes to come from somewhere geometric, these come from somewhere geometric. Okay, and that's, now I can tell you about our main result, keeping a couple of definitions for later. So the first thing that we prove, so we pick any Coxeter element in Sn. I'll tell you what those are in a second. And what we show is that the permutahedron can be decomposed into a bunch of Bruhat interval polytopes. And this decomposition is in fact a subdivision, so it's very nice. I'll say what a subdivision is in a second. And which Bruhat interval polytopes should you choose to decompose your permutahedron? Well, they're indexed by pairs of permutations. The first one is U, the second one is C times U, and they have this special property that the second product is length additive. So the length, oops, I don't know what just happened. A perils of technology. Let me reshare my screen.
Simple question. So is it clear that this Bruhat intervals, they are matroids?
They do happen to be flag matroids. They're even flag positroids. I think it's not too hard to see this. I'm sorry?
So it's easy to see? Because from definition, it's not so clear.
I think it's not too bad. I don't off the top of my head remember a proof. Sorry, I'm trying. Can you see my screen now?
Back now.
Yes.
Okay. Great. All right. Okay, so I was in the middle of saying, I think, okay, so we talked about this theorem. You pick a Coxeter element. I haven't told you what that is yet. You obtain a subdivision of the permutahedron, and the permutations that you're using, like the Bruhat interval polytopes you're using, the way you pick them out is you're picking those permutations U, where C times U is length additive. Okay, so that's the result. And now let me fill in what's missing. So first, what's a Coxeter element? Okay, so a Coxeter element is just a product of all of the simple transpositions in any order using each simple transposition precisely one time. Right, so simple transpositions are the ones that swap I and I plus one. And Coxeter elements, I'm just using each of them exactly once. So for n equals 4, I have 3 simple transpositions, S1, S2, and S3. And here are my Coxeter elements. So I've got S1, S2, S3 in that order. I also have S1, S3, S2, which is the same as S3, S1, S2. And then I have the inverses of both of those. So I've got 4 Coxeter elements. And in general, there are 2 to the n minus 2 Coxeter elements in Sn. So this theorem is producing for you 2 to the n minus 2 different subdivisions. Okay, and then what is a subdivision? So like I said, it's a kind of decomposition of this big polytope into littler polytopes that's particularly well behaved. So, okay, so in general, if I've got some d-dimensional polytope, and I've written it as a union of other d-dimensional polytopes, call those Qi. This is a subdivision if for all of my smaller polytopes, they intersect in a common face. Okay, so this is saying that for one, their interiors don't overlap, and the way that their boundaries touch is kind of well behaved. So if you haven't thought about this before, here's some non-examples of subdivisions. So this example is like very bad because two of my pieces, Q1 and Q2, they intersect in this triangle, and that triangle is definitely not a face, right? It's not an edge or a vertex of either of the 2 quadrilaterals, Q1 or Q2. Okay, and then you can have more subtle bad behavior, right? Where in this thing, one of my, like, I take this piece, this quadrilateral Q1, if I intersect it with this piece, the triangle Q3, I get just this line segment. This line segment is a face of Q3, right? It is an edge of Q3, but it is not an edge of Q1. It's just a part of an edge. So that is also bad, not a subdivision. But 2 pictures that we've seen before, these 2 things are subdivisions. And actually, the smaller pieces that I'm using, they are Bruhat interval polytopes, right? They're exactly the ones that I showed before. And in fact, these 2 subdivisions are the 2 subdivisions we get from this theorem when n is equal to 3. So yeah, this is like the babyest illustration of the theorem. Okay, so I have theorem 1, so I also need to tell you about theorem 2. And maybe I should actually pause for questions. Yeah, go ahead.
Some small questions. Coxeter elements, they are different. So some are nice, for example, bipartite. Then power of Coxeter is reduced decomposition. So is any difference if you have some nice Coxeter element and not nice?
Kind of. I'll talk about one difference at the end, but it's mostly actually just, yeah, it's not really like there's a distinguished, yeah. Okay, I think the answer to your question is basically in some way, like all Coxeter elements are just giving us something different, and it's not really the case that one class is much nicer than another class. Yeah.
Okay, thank you.
Yeah. Okay, so right, let me just briefly mention theorem 2. So this is sort of the geometric side, and I'm going to be really vague. So the geometric counterpart of theorem 1 is the following. So again, we pick a Coxeter element. And what we have is a degeneration inside of the flag variety of the permutahedral variety to a union of Richardson varieties. And the thing you should be picking up here is that the union, the permutations I'm taking the union over, is the same as the permutations I'm taking the union over here. So if you like this sort of thing, what's going on between these 2 theorems is essentially we're taking the moment map image to go that way. Okay, and because we have this degeneration, we also obtain formulas for the class of the permutahedral variety as a sum of Richardson classes. And again, the sum is over exactly those permutations that are showing up in my union up here. Okay, so I'm not going to say anything else about this. I'm really going to stick to the combinatorics for this talk, but you should just know that there's sort of a geometric counterpart floating around in the background.
And what's permutahedral variety? Just toric variety of the permuhedron?
That's right. And I'm thinking about it inside of the flag variety. So really, I've taken a generic point in the flag variety, I've taken its torus orbit, and then I've taken the closure. Okay, so that's our result. And now I should explain to you, like beyond, I don't know, it's just kind of nice. I should explain to you like why we were thinking about this, some motivation for trying to understand these kinds of subdivisions. So the motivation, one motivation is, okay, actually, I realized I forgot to say something. So one thing that I should have mentioned is the subdivisions that we obtain, they're actually very nice. They're what are called regular subdivisions, which just means they're particularly well behaved. Okay, so one motivation for this is that regular subdivisions of the permutahedron into Bruhat interval polytopes, so exactly the kinds of subdivisions we have, they've been studied before and in some sense characterized. So if you combine work of Boretsky with work of Joswig, Loho, Luber, and Olarte, you get that these particular kinds of subdivisions are in bijection with the cones of the positive tropical flag variety. Okay, so Melody talked a bit about tropicalization. You don't need to know what she talked about to understand this. So you should think of this as being a kind of combinatorial shadow of the flag variety. But concretely, so it has some definition. I'm not going to give it to you. Concretely, what is this? It's going to be a polyhedral fan inside of some big vector R to some big power, and it's got some cones. Those cones are exactly in correspondence with these subdivisions. So concrete example, here's a picture of this positive tropical flag variety for n equals 4. Okay, so this is a polyhedral fan in R3. And what I've done is I've intersected it with the sphere. And I'm showing you how it intersects with the sphere. So buried deep inside of the sphere is the origin. And then from the origin, for example, there's like a ray coming out and it hits the sphere right here. And so that's what this point is. It's a ray in my fan. And then this bit here is going to be some like two-dimensional, sorry, I'm trying to go back. I'm going into the sphere with this. So there's like a two-dimensional face cone of my fan, which starts at the origin and sort of goes out like this, and it hits the sphere exactly in this edge. And then similarly, like here's a three-dimensional, there's going to be a three-dimensional cone of my fan, which hits the sphere exactly here. So the blue and red stuff is what's coming towards you. And then there's a gray cone that's going to the back. So that's why it's gray. Okay, so this is the positive tropical flag variety for n equals 4. And if I pick any cone in here, so like if I pick this cone, which is actually like a ray coming out from the origin, that will give me a regular subdivision of the permutahedron into Bruhat interval polytopes. And this is what it looks like for that particular cone. And then if okay, so that was for this ray. If I walk a little bit in, so if I move, instead of thinking about the ray, to this two-dimensional cone, which happens to contain that ray, I get a different regular subdivision, and it looks like this. You can see what I did is I refined my subdivision. So I took some polytope that was in here, and then I kind of cut it into two pieces. Okay, and then I can keep going. So I can also walk kind of from this edge into this three-dimensional cone. And then I get a subdivision that looks like this. So again, I've done a refinement. It's a little harder to see. I've actually taken all three of the polytopes here and I've cut them further into pieces. Okay, so that's how the correspondence works. Each cone in here gives me a regular subdivision of the permutahedron into Bruhat interval polytopes. Okay, so great. This sort of means that we completely understand the regular subdivisions into Bruhat interval polytopes because we have some other object, which I didn't define for you, but can be defined, that parametrizes my regular subdivisions. So in some sense, you could be like, great, we're done. We don't have to think about this problem anymore. But I guess my perspective is that we're not done. Actually, we barely know anything. And so we should continue to investigate this problem. So one thing that we don't know, for example, is basically anything about the combinatorics of this polyhedral fan. So we don't know how many maximal cones there are. We don't know how many rays there are. We don't understand, so we don't have an indexing set for the cones. And we don't know how to tell if two cones are adjacent, except to stare very hard at their equations. So even though you can say, oh, well, the rays, they're going to correspond to these coarsest subdivisions. We don't actually know how many coarsest subdivisions there are, or really what they look like. Right. And so then, right, this is the next part where little is known. So if you hand me a cone of the positive tropical flag variety, I have to, like, really, I have to ask a computer to tell me about the combinatorics of the corresponding subdivision. So just looking at the cone, I don't really know which Bruhat interval polytopes are in the subdivision or how they're connected. So one thing that our theorem does is it gives us a bit more information about some of this. It's definitely not exhaustive. What theorem 1 is doing is it's actually telling us 2 to the n-2 finest subdivisions into Bruhat interval polytopes. So it's telling us about 2 to the n-2 of these maximal cones in the fan. And for n equals 4, it's exactly these 4 highlighted cones. So those 3 in the front and then the gray one in the back. So for these particular maximal cones, we know exactly what Bruhat interval polytopes are in the subdivision. Another thing this tells us is that the positive tropical flag variety has at least 2 to the n-2 maximal cones, which we didn't know before. I mean, this is like a very bad lower bound, right? The number is surely like way, way bigger than this, but at least we know there's like an exponentially many maximal cones.
Melissa, I'm sorry if you mentioned this. The positive tropical flag variety is a polyhedral fan, but do you know that it's not polytopal?
Oh, like is it the normal fan of a polytope?
Yes, sorry, that's my question.
Yeah, so I think it is not known whether or not it's I'm trying to think of I think there there's some subtlety here, which is that the positive tropical flag variety is really a set, and you can endow it with the structure of a fan. So it's like this is actually a set, which is the support of a polyhedral fan. And there's some choices you can make about which fan structure you put on it. Some fan structures, I think, definitely are polytopal. The particular one that I'm talking about, which sort of matches up with the combinatorics of the subdivisions, I think it's not known if that is polytopal or not. In this particular example, it is. I think it's the normal fan of the associahedron, but that's very special to n equals 4. Okay, so I think, so I had another slide. Oh, go ahead.
So you consider permuhedron like a sum of roots ei minus ej, so just intervals. So what combinatorial model you consider? So because you can we can look at the permutahedron just a sum of segments, so it is zonotop. And then I return to my first question. So you told me that it is matroids, but it would be not matroids. It would be just generalized matroids, I think.
So the Bruhat interval polytopes are flag matroid polytopes. So I think maybe that corresponds to what you're calling generalized matroids. I'm not sure.
But what? So you consider just sum of segments? So what kind of model for
the Bruhat interval polytopes are not usually zonotopes?
No, for polymatroid. So for permutahedron, permutahedron have several implementation. For example, you can take sum of segments 0 ei minus ej.
So I told you, I think before, exactly which permutahedron I was considering, which was exactly the convex hull of the permutation vectors. I'm going to keep going because I think we should, if you have more questions, maybe we should talk about them after the talk.
Okay.
Okay. So this is a little bit of motivation, kind of trying to understand this correspondence a bit better. I have another slide about motivation, which I think for the sake of time, I'm going to skip. So let me tell you a little bit more about the combinatorics of these subdivisions. So I told you which polytopes were in them, right? So we just look at those U's where C times U is length additive. But you might also ask, well, how many pieces are there? In my slide that I skipped, there's some more motivation for asking how many pieces are there. That's fine. You should just think this is a good combinatorial question. And the answer is pretty nice and not that hard, but also some interesting numbers pop up. So, right, so the question we're asking, so we have that this is a subdivision of the permutahedron, and we want to know how many polytopes are actually in our union. How many pieces do we need? Okay, and the answer depends on C, right? Because we're asking how many permutations are there where C times U is length additive. It definitely depends on C. If you're a connoisseur of the symmetric group, you recognize that that number, the number of permutations where C times U is length additive, that's a weak order interval. I forget if it's left or right. It's the one above C. So I'm just trying to count the size of a certain weak order interval. And you can do this using inversions. So to figure out how many polytopes are in this union, I can start with my Coxeter element C, and I can construct its inversion poset, which is just keeping track of the inversions of C. And the number of permutations where C times U is length additive is going to be just the number of linear extensions of the inversion poset. Okay, what do these posets look like? Because we're looking at Coxeter elements, the inversion posets are very special. So they always look kind of like this. There's sort of only 2 levels, 2 ranks. And what you'll get is you'll get a zigzag. And then from each peak and valley of the zigzag, you can choose some non-negative number of like dangling elements that either go down from a peak or up from a valley. That's always what the inversion posets look like. So, and of course, if you choose different C, what's going to change is like the length of the zigzag and also how many dangling elements you have. And so looking at this, you can see there's kind of the 2 extremes happen when your Coxeter element is, okay, so one extreme is when your Coxeter element is kind of the standard one. So when it's just the product of simple transpositions in order, or the inverse of that one. And in that situation, the inversion poset turns out to be a claw, or maybe it's dual. And okay, how many linear extensions are there of this poset? Well, we've got n-1 things on the bottom, and those are completely free. And so there's n-1 factorial linear extensions of this poset. At the other extreme is this bipartite Coxeter element that was mentioned before. So this is the one where you take transpositions, the simple transpositions indexed by odd numbers. And then after that, the simple transpositions indexed by even numbers, or the inverse. And in that situation, the inversion poset is just the zigzag. You don't have any dangling things at all. And the number of linear extensions is an Euler number, also the number of up-down permutations. And well, here are those numbers. And so you can see, okay, so they start off the same. So I think because the 2 kinds of elements actually start off the same. And then as n gets bigger, you get bigger and bigger gaps between the number of pieces in this subdivision and the number of pieces in this subdivision. So you get kind of, and then you should imagine you've got lots of stuff in between, right? Because there's lots of Coxeter elements that interpolate between these 2 extremes. So yeah, one thing that this is telling you is that so all of these subdivisions are finest Bruhat interval subdivisions. So you can't cut any of the polytopes and get another Bruhat interval subdivision, but they have wildly varying sizes. So being finest by inclusion is very different in this circumstance than being having minimal number of pieces. Okay, so I'm going to finish by just kind of saying one more thing. So I told you the symmetric group version of our results, but we also have versions for kind of arbitrary types. So you fix your semi-simple Lie group G and you let W be its Weil group. Then kind of exactly the same combinatorial statement. For every Coxeter element, you have a subdivision of the W permutahedron. And okay, I've switched notation a little, so this union looks different, but I promise it's actually the same as the other union I was taking. So very similar kind of, you know, we want length additivity. That's what tells us which polytopes to put in our union. And then we also have kind of substantially more general geometric result, where actually instead of choosing a Coxeter element, you just pick a Weil group element, V. And then in place of the permutahedral variety, you have what's called the Deligne-Lustig variety. And the general version of our result is that we have a degeneration of the Deligne-Lustig variety into a union of Richardsons. And so we have these class formulas for the Deligne-Lustig variety as a sum of Richardson classes. And to go now in this more general setup, to go from theorem 2 to theorem 1, well, you need to pick V to actually be a Coxeter element, and then you apply the moment map as before. Okay, so this was just for experts. In case you're interested, the results hold in a bit more generality. But yeah, so it wasn't meant to be comprehensible. I know that's a bad note to end to talk on, but I guess I'll end there. Thanks so much for listening.
Let's thank Melissa for a very fun talk.
And in the first theorem, so P tilde EW0 is what? It's just sum of intervals with positive roots?
Yeah, so this is, I take W and let me do this in another color. Yeah, so I take W and I act on rho, the sum of the fundamental weights, and I take the convex hull. And then that's also what these P tildes are, is instead, so I take the interval WWC, I act on rho, and then I take the convex hull.
Thank you.
Yeah.
You have a tropical flag variety analog for this part of the story?
No. So we also actually, in general, so like for type A, I put in regular here, right? I had like this, but actually for this part of the story, we don't know regularity in general. So yeah, those two things might be related. I think people are working on positive tropical flag varieties in other types. And all of the examples I've done seem good. Like they don't tell me that there like shouldn't be an analogous result in arbitrary types, but no one has actually worked it out. Federico.
Sorry, I have to.
Oh, okay, he's gone.
While you're on this slide, can I also ask, so this degeneration, is that only giving you ordinary cohomology formulas?
Okay, so I am not among the three of us, I'm not the correct person to ask. I believe everything is equivariant, p-equivariant, and so it also gives equivariant cohomology schemes, and I think it also gives K-theory, but you should actually check with Alan or Mario.
Sure, but they're not here.
They're not here.
Okay, Federico, get back.
Yeah.
Okay, now I'm back. Melissa, wonderful talk. So you said that all of these are finest subdivisions. You cannot refine
That's
them
right.
further using Bruhat interval. Can you say anything about the opposite case? You mentioned something about the coarsest possible Bruhat interval polytopes. Naively, I will expect that they have two, but do you have examples where it's multiple of them?
So I think so in the paper of Boretsky and Williams, which I maybe failed to mention. So yeah, my extra motivation slide was there's like kind of a more general story due to Boretsky and Williams generalizing this correspondence. Anyway, in their paper, they do some computations of both finest and coarsest subdivisions for n equals 4. And I think, and they compute F vectors. So their table should tell you, like,
Okay.
and their table is as much as anyone knows, I think. So you should look at that paper and then you will see the answer to your question.
Okay, thank you.